Today, we are diving into one of the most elegant, I mean, truly brilliant ideas in all of chemistry, retrosynthesis. You can think of it as the secret logic, the master blueprint behind how we create everything from life-saving medicines to the advanced materials inside our phones. Let's peel back the layers and see how it all works. Okay, so picture this. You're in a lab. On the shelf, you've got a bunch of simple, basic chemicals. And your goal is to build that. A complex, very specific molecule. So how do you do it? How do you create a reliable step-by-step plan to get from those simple starting blocks to your finished product? Seriously, without a solid plan, it's kind of like trying to build a skyscraper with no blueprint. You're just stacking bricks and hoping for the best. So to crack that puzzle, here's our roadmap. We're going to start with the old, kind of confusing way of thinking about this problem. Then we'll get to the aha moment that changed absolutely everything. We'll learn the lingo, check out the key strategies, walk through a real-world example, and then finally, we'll see why this way of thinking is just so incredibly important. All right, first up, let's really get our heads around the problem chemists were up against for decades. Trying to build a molecule forwards is like being dropped into a massive maze. I mean, a maze with thousands of possible turns. You know where you want to end up, but almost every path you take just leads to a dead end, or even worse, some are completely different. You know, the traditional approach was basically a guessing game. Chemists would stand there and ask, okay, if I mix chemical A with chemical B, what's going to happen? And yeah, sometimes it worked, but most of the time it was just this incredibly frustrating process of trial and error. It felt more like an art than a science, you know? It really relied on a chemist's intuition and, let's be honest, a good bit of luck. And then, the revolution, this huge shift in thinking. What if, instead of trying to build forward into a fog of possibilities, we started at the end? What if we looked at our finished product and worked backward? This is just like a master chef tasting some incredibly complex dish and being able to tell you exactly what ingredients went into it and in what order. It's genius. And this slide, it just lays it all out, doesn't it? The mental shift is huge. Forward synthesis is all about asking, what can I make? It's exploratory. But retrosynthesis, that's all strategy. It starts with the target you want, and it asks a much, much more powerful question. What is this made from? And just like that, the path changes from a hopeful guess into a logical, reverse-engineered plan. Now, the person we really have to thank for turning this brilliant idea into a system is chemist E.J. Corey. See, he didn't just have the idea. He created a systematic, logical framework for it. He essentially wrote the universal cookbook that lets chemists everywhere think like that master chef and deconstruct any molecular dish they come across. All right, so to use this incredible cookbook, we need to learn the language. Retrosynthesis has its own specific set of terms that let chemists talk about these backward-thinking plans clearly. And don't worry, we're going to stick with our chefinology to make these super, super easy to get. So the first and most important word is disconnection. Think of it like a chef tasting a complex sauce. In their mind, they're separating it into its core parts. You've got the savory base, that acidic kick, the herbal notes. A disconnection in chemistry is that exact same idea. It's an imaginary, strategic cut we make in our target molecule to break it down into simpler, more manageable pieces. Okay, so when our chef identifies a flavor in that sauce, they're not thinking about the actual physical lemon. They're thinking about the pure concept of lemony tartness. Well, that's a synthon. In chemistry, it's the idealized, perfect building block that we get from one of our mental cuts. Now, this is crucial. A synthon isn't a real chemical you can hold in a bottle. It's the perfect theoretical piece of our puzzle. So you might be asking, if a synthon is just an idea, how do we actually make anything? Great question. And that's where the synthetic equivalent comes in. This is the real-world, off-the-shelf chemical that you can actually go buy and use in the lab to do the job of that idealized synthon. It's the actual lemon, the real stick of butter, the sprig of thyme that our chef goes to the pantry to grab. Okay, let's put it all together with our lemon herb chicken. It makes so much sense this way. We start with our target dish, right, the finished plate. We perform a disconnection by mentally separating the sauce. This gives us our synthons, the idealized flavors of lemony and buttery. Finally, we go find our synthetic equivalents, the real ingredients, an actual lemon and some butter that we need to cook the dish. See? It's a recipe. So now that we've got the language down, let's talk a little strategy. Just like a chef has different knife cuts for different jobs, a julienne, a dice, a mince, a chemist has different kinds of disconnection strategies. And the type of cut you make all depends on what part of the molecule you're trying to simplify. A one-group CX disconnection is usually the simplest one. Think of it like scraping the frosting off a cupcake so you can deal with the cake underneath. Easy enough. A one-group CC cut is a little more involved, maybe like separating the burger patty from the bun. But when you get to a two-group disconnection, well, now you're dealing with a much more complex system. This is like deconstructing a multi-layered cake. It takes a much more sophisticated approach to pull it apart correctly.
Okay, enough with the theory. Let's see what this looks like in the real world. We're going to take all of these concepts, disconnections, working backwards, the whole shebang, and actually apply them to create a real step-by-step blueprint for building a molecule from scratch.
Let's try this with p-bromoaniline. Now remember, the key is to think backwards. A chemist looks at this and immediately sees that amino group, the NH2, and they know from experience that it can be reliably made from a nitro group, an NO2. So our first backward step, our first disconnection, is to just imagine swapping that amino group for a nitro. That gives us p-bromonitrobenzene. Now we ask the same question again. What's this made from? Well, we know we can add a nitro group to plain old bromobenzene using a really common, well-known reaction. And just like that, boom, we worked our way back to a simple, cheap, readily available starting material. We now have a clear, logical, and efficient blueprint.
So we've seen the logic, we've learned the language, and we've walked through an example. But why does this one idea, this simple flip in perspective, matter so much? How does this actually change the real world?
It matters because this strategic thinking is the engine that drives modern chemical innovation. I mean, this is how chemists design everything from brand new antibiotics to cutting-edge cancer treatments. It's the logic behind the advanced materials in our smartphones and electric cars. It also makes everything we do way more efficient, creating less waste and using cheaper materials. It is, and this is no exaggeration, a cornerstone of modern science and technology. When you boil it all down, retrosynthesis did something truly incredible. It took the messy, intuitive, and often frustrating art of building molecules, and it transformed it into a logical, predictable, and incredibly powerful science. It gave chemists the blueprint they had been missing all along. So, let's end with a molecule a lot of us know and love, caffeine. Now that you understand the logic of working backward, now that you can think like a master chef, take a look. What's the first strategic cut that you would make?